Okay, in a previous video, we showed how to compile and run Verilog simulations, and also how to view the results in GTK waves. And then we viewed the Blinky Verilog code that would get instantiated into an FPGA. That's this code here. And today we'll cover the Blinky Testbench code, which we'll use to run a simulation of the Blinky module. Um, The code is on GitHub here. Um, let's see, we start off with like module TB, which is a test bench. Give it any name you want. Starts with module and then end module keyword, closes it out. There's two types of signals, variables that we have to concern ourselves with. Um, so registers, column registers, if the test bench is driving an input signal of the module being tested. And if it's an output, call it a wire. It's a little tricksy, not too bad. Um, let's see. And then one of the things that the test bench needs to do is to generate a clock, which is the heartbeat of the module being tested. Every time there's a rising edge on this clock, the module is going to do something. And then it waits for the next rising edge, and then it does it again. And so that's the basic structure of how the Verilog module operates. Wait for a clock, do something. Wait for a clock, do something. So in this case here, we defined a register, called just a variable called system clock 100 megahertz. And we initialize it to 0. Then we have this always block, and that means that it's always running. And so it runs, it's going to wait, in this case, wait five ticks, or in this case, 5 nanoseconds. Then the value of the clock is going to get inverted. So basically it toggles the clock. And then it goes back up and it comes down. It waits another 5 nanoseconds. And it toggles the clock. Then it goes back up around and it waits 5 nanoseconds. So essentially that's making a clock that's high 5 nanoseconds, low 5 nanoseconds for a 10 nanosecond period, which is a 100 megahertz clock. So that's that signal. And then you need to instantiate the block that you want to be testing. In this case, it's Blinky is the name of the module. I give it an instance name, in this case of U.dot. Dot stands for like device under test. Sometimes it's called UUT for unit under test, or you could just call it U-Blinky if you wanted to. Why not? I think I prefer that in a way. I wonder if that's going to break anything. I don't think it should. Control S. All right, so I'll just call it something. So this is the instance name. And then these are all the inputs and output signals. And so it follows like a named parameter scheme as opposed to, you could also use an ordered parameter scheme. We tend to end up having a lot of inputs and outputs to a blocker. That's potential. So almost always for human generated code, you'll have the named approach. Some tools for netlist will use the ordered signal parameter approach. But in this case, the syntax is a dot followed by the internal module signal name followed by the external module signal name. So Blinky calls its internal signal clock, but in the outside world here, it's called system clock 100, which is this guy right here. So this guy is driven into here and is toggling and causes Blinky to run every time this signal has a rising edge, which we saw in the last video. Similarly, we've got the system reset end, and that is driving the signal reset end inside of Blinky, which will initialize Blinky. So those are the two input signals. You might even want to put a comment out here. Like, but and then LED is output on the module. And so this is output by Blinky and the Blinky module, and that eventually gets connected to some general purpose I/O pin that would eventually get to on the board an LED and cause it to turn on or turn off. All right, so that's top level setup type of stuff. And then you have like a main initial block. And so this is like the main function or main method. And so there's a difference between an always block, which is always running, like this guy keeps wrapping around, and an initial block. An initial block just runs one time. So it starts up at, at the beginning of the simulation, and then it runs through to completion. And then when it gets to the end, where is it? Where is it? Right at the end, right here. I think I'm trying to comment. And main best initial block. Then when you get to the end, it'll stop. In this case, we have a $finish command, which causes the entire simulation to stop. So we never really get to the very end. But that's okay. So anyway, in this initial block, it starts going. So we have like, you just define like the variables that you want to be using in your test. So like II is just, I usually use II instead of I as a counter. I prev is the previous value of it. I delta is the difference between the current II and the previous II. Fail counts, I'm counting the number of failures. First time means the first time through some internal loop. And GPI LED2 is just like a copy of GPIO LED. And so it's just like a delayed version so you can see an edge. Um, yeah, that's about it. One thing to note is that you can define your signals, your variables, your registers, whatever you want to call them, anywhere in your code as long as it's before where you use it. So like this kind of stylistic thing. Some people like to have everything at the top. Some people like to embed it internally so that you can, keep your code close together. Yeah, you do what you think is best. So here are some signals that we're going to be using in our test bench. And then in Verilog, instead of a printf, they have this dollar display. But it works very similar to the printf in that you have this what do you call it? Some sort of command string that or format string. And then you got this $D, which prints out an integer, and it's printing out II. Later on down in here, you'll have a display where we have like the format string is nanoseconds. It passes, %D, 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 and here we got the string of integers that get printed out. So it's very similar to C, except they call it dollar display instead of dollar $printf. A lot of very keywords in Testbench to style keywords in Verilog tend to start with a $sign. So you can see a dollar display here. This dollar finish. You got this dollar dump file and dump vars, which we'll talk about in a moment. So they got a few dollar things, but shouldn't, just view this as a printf. Dollar time is also a keyword, so it tells you what simulation time it is. So it's bumping up in nanoseconds. So it's not wall time, it's simulation time. So here, this line here is just waiting for a system clock. So at pause edge, system clock, we advance. So it waits at this line until eventually it sees a positive edge, a rising edge on the system clock, which happens as we saw here. Here, it'll happen like every 10 nanoseconds. So 5 nanoseconds low, 5 nanoseconds high. So every 10 nanoseconds, you get a falling edge. Every 10 nanoseconds, you get a rising edge. Yeah. All right, so this is that. And then, so basically what this was doing was waiting for clock edge. And then it decided to drive the reset signal to low, which resets, which this gets propagated into the instantiation. That signal goes into the instantiation. The next clock tick that comes along, the block would then reset itself and go to initial state. Here is a repeat 10. The repeat command is basically it does the same, does this 10 times. So in this case, it's waiting for a clock and advances, repeat. So it waits for 10 clocks. You could also throw in, if you want to, like begin, something like this, and so if you prefer that format, that's okay. So this format where it's so it turns on. So in this case, it's turning on the reset. I mean, it's deasserting the reset n because it's a low active reset. In that low active reset, the underscore n is a common nomenclature. Sometimes it's underscore l. To indicate it's a low active signal, meaning that when reset is low, the block is reset, the Blinky is reset. Now we're waiting 10 clocks for whatever reason. And then we have for loop. We're going and waiting. Where essentially it's C-style for loop, doing it 10,000 times. Why not? It's a large number. The only difference really is that you can't do an I++. Right? You got to do an I equals I plus 1. No biggie. In this case, we're assigning GPIO LED, which is an output of this block, Blinky, to GPIO LED2. Then we're waiting a clock, and then if this guy, GPIO, the output of GPIO is different from LED, means it changed, then we're going to fall into this little test thing. Oh, we said, oh, we changed Blinky. And so what I'm doing is I'm looking for I want to know how long it took to change from the previous one to the current one. It's a test thing. I don't know. So I wanted to see that every 256 clocks it would toggle. So I compare that, and then I compare this delta value with 256. And if it is, then I say, oh, great, it passed. If it didn't, then I say, oh, it failed. And I also have a special case of this first time. It's the first time in the loop, and it might not be 256. It might be a little less, a little more, because we got these goofy repeats up here. So if it's not the first time, then we fall in, we bump the fail count, and we print out that it failed. And then we also change first time to 0, meaning after the first time through this loop, then we no longer the first time. And I prev, and then let's see, we're just recording the previous time that we captured it. So that's, a very C-ish type of structure here. Important thing here is, though, in this loop, the advancing time here. This is probably not needed. So I have it there. Let's get rid of that. Sometimes it's a good idea to have it. Right? And what that does is it delays for 1 nanosecond, a trivial amount of time. Let's get rid of it for now. See if the simulation still works. So we're going to do that. And then basically we start wrapping. Wrapping up. We wait another 20 clocks. And then we check if fail count is 0. If it is, we say, hey, it passed. If it's not 0, then we say, ooh, it failed. And this many fail count tests failed. And that's it. Get to this in just a moment. I just want to go to see if I broke anything here. So // compile. Great, it still compiles. / run. See if I broke anything. Still works good. Okay. So those little changes I made did not break anything. This block here is so like dump file tells it what file you want to write the waves to. And dump vars basically means this is, you start at the very tippity top. This is the syntax. Don't get hung up with it. Just copy this. And I think that will get you, if you follow this format, you can test almost any block. It scales very nicely. So I think that's probably about all I've got. And yeah, so I'll shut it down.